So hello everyone, good morning. Welcome to the Gate Academy. Welcome to the Gate Academy. So today in this lecture we are going to start. Today in this lecture we are going to start the new syllabus, the new edition which has been added for Gate 2021 syllabus, the gas turbine and steam turbine, the gas turbine and the steam turbine. So in this lecture series, what we are going to do, we are going to cover these new additions in the Gate 2021 examination, the new addition in the Gate 2021 examination. So what has been added as far as thermodynamics part is being concerned is the gas turbine and the steam turbine, the steam turbine and the gas turbine. So first of all, I would like to welcome you all on the Gate Academy. I like to welcome you all on the Gate Academy. Okay, so before beginning with this thing, I want you to subscribe and like the Gate Academy channel so that you will get good videos, good technical videos that will help in your preparation. That will going to be help in your preparation. So firstly, briefly, let me tell you about who am I. Okay, but firstly, briefly, let me describe who am I. Okay, so as you can see on the screen, my name is Uma Shankar Tripathi. My name is Uma Shankar Tripathi, and currently I am a PhD scholar at IIT Roorkee. People usually call PhD scholars like research scholars. Research scholars. Okay, so I am doing my PhD from Indian Institute of Technology Roorkee. Okay, and I am in my 4th year. Okay, so before PhD, I have completed my MTech from IIT Roorkee itself. From 2014 to 2016. So the year of completion of my MTech is 2016. Okay. So as you all know, for going into good morning, Srihari, good morning, Pradyuman. So as you all are aware, for getting admission into IIT Roorkee MTech, one need to give this examination for which you are, Amesh, good morning, for which you are preparing for. So I have given GATE 2014, in which I got 65.66 marks. Okay, obviously in 100, and I gave this examination in ME branch. Okay, and my all India rank was 960. On the basis of this rank, I took admission in IIT Roorkee in MTech program, in master's program, as you call it. Okay, so in GATE 2015, again I have given the GATE examination. In 2015, again I have given the GATE examination, and I had 77.02 marks. An all India rank of 643. All India rank of 643. Okay, so this is the history of GATE of mine. This is my GATE history. Okay, how many times I have appeared and what ranks, what marks I have got. So in GATE 2015 also, I appeared in mechanical branch, in ME branch. So I hope you all are preparing for the GATE examination. So let me tell you a little bit discussion we will do over here about this part, why I am mentioning all the numbers, marks over here, because see, I am a BTech pass out of 2011. I have completed my BTech in 2011 from a private college. Okay, so after BTech I was working. So in GATE examination 2014, so while I was preparing, so let me give you some data first. So in GATE 2003, the person who is getting this mark 65 something would have got all India rank below 100. You can check on the Google as well. In GATE 2014, if I tell you, if someone has got this much mark, around 77 marks, he would have got all India rank under 100. Okay, so why I am telling you all this? Just to make you know that some marks are so much important in GATE examination. Like in GATE 2014, if my marks were more 5 or 10 marks more, my rank would be below 100, and I would be joining IST Bangalore or IIT Bombay or somewhere. Okay, because in my job I was already in PSU, so I hadn't I don't wanted to go to the PSU again. Okay, so this 65.66 mark, if plus 10 marks I would have achieved, I would be in IST Bangalore or IIT Bombay. Okay, In GATE 2015 again, if I had 10 plus marks, I would have obtained a rank below 100. Okay. So see, what I'm trying to say here is that every single mark in GATE examination is important. In GATE examination is important. Why is it so? Because 5 marks, 6 marks, 10 marks can shift you from IIT to NIT, from ISC to IIT, from IIT to NIT, and PSUs will be out of question. PSUs will be out of question. But it will happen only when you are achieving, you are getting marks around 60, 65. It won't happen when you are having marks around 25, 30. If you are getting 25, 30 marks, then there is no problem. Okay. So, what we are going to cover here. This was a brief introduction about me. So, Raj, I will answer your question, and Frozen Race, I will also answer your question. But firstly, I would like to ask, anyone want to have some query about it, this GATE structure or anything, so that we don't have to come back to it anytime later. Anything? So before beginning with this, there is a request that we are live here. So those students who are live on chat, they must interact with me. Okay, so that this should appear like we are doing a live class. Okay, so you will give your feedbacks on the chat. You will give your feedbacks on the chat. You will ask questions on the chat, and I will certainly reply to you. So this is a structure what we are going to cover in this series. Okay. So see, as I said, we are going to cover what? We are going to cover new syllabus, new addition. Okay. So we are not covering whatever already was there in a syllabus. Okay. Whatever already was there in a syllabus, although we will briefly discuss it. We will briefly discuss these things. But here our purpose is to cover whatever is being added in GATE 2021 examination. Okay. So we are not going to discuss whatever was already in the syllabus. Okay. Like we will be discussing a little bit of Rankine cycle, because see, you won't be able to understand all these things if I totally ignore that. Okay. So that total ignorance will not be there. Total ignorance will not be there. But what we are going to cover is listed over here. Okay. Introduction to steam turbine, flow through nozzles, impulse turbine, reaction turbine. Then we will see gas turbine cycle, actual gas turbine cycle, Brayton cycle, ideal Brayton cycle, components of gas turbine cycle. So this is all I have written here, which is into the new syllabus, not the old one. Okay. So now we are going to begin this with this new syllabus. So as you are saying, sir, what is the expected weightage from new syllabus? So let me tell you very frankly, question may come, may not come. This is not in our hand. What is in our hand? That we can prepare for it. That question, if the question comes, then we will be able to answer. Right? So this is the part of the power plant thing. So till GATE 2020, the power plant part was asked in 2 marks or sometimes 4 marks. The whole thermodynamics along with RAC and power plant IC engine combined is mostly asked between 12 to 16 marks. Okay. So from in that margin, you can expect a new question from this new syllabus. Okay. Ganesh, we are going to do that. We are going to introduce the steam turbine when we are going to begin with the lecture. Okay, so this was the brief introduction, what we are going to do here. This was the brief introduction, what we were going to do here. So if there is anything you want to ask from me, now you can ask from me if there is anything. If there is anything you can ask from me about this. So I think now you can see the OneNote on the screen. You can see the screen, yes or no? Yuvinder, I have written the gas turbine cycle, but the syllabus is gas turbine, that is true. But once you go through the steam turbine, you will come to know that the gas turbine is exactly same as the working of steam turbine and gas turbine. So we are not going to discuss the same thing again and again, right? And actual gas turbine cycle, was it there in the previous GATE syllabus or not? Was it there? So it wasn't there. Is gas turbine cycle and gas turbine are same? No, they are not same. Gas turbines are the part of gas turbine cycle. Okay, so you will come to know, you will get to know. So firstly, our topic we are going to begin with is steam turbine. Is steam turbine. Okay, the name of our topic is Introduction to Steam Turbine. Right, introduction to steam turbine. So actual gas turbine, Yugender, as you are saying that you haven't read it because it was not in the GATE syllabus. So we are going to read that. We are going to read that. Don't worry about it. Don't worry about it. Okay. So steam turbine we are going to begin. So firstly, let us have the introduction of steam turbine first. Let us have introduction of steam turbine first. Okay. So where are you using this steam turbine? So I think you all are aware of this steam power cycle. See, as I said, I am considering that old syllabus, you know, steam power cycle. Are you aware of it? Are you aware of it? Where we have studied the Rankine cycle. We have studied the Rankine cycle. Okay. We have studied the Rankine cycle. Okay. So what we have studied in the Rankine cycle? What we have studied in the Rankine cycle? Can you tell me that? What we have studied in the Rankine cycle? Just a moment. There is some technical problem here. So, okay. So Rankine cycle you might have heard and might have seen. So what is there in Rankine cycle? What is the basic power steam power cycle? What is the basic of steam power cycle? So it was already there in the GATE syllabus. So we will very quickly see what we have already studied and what we are going to add in this lecture or in this lecture series. Okay. So steam power cycle, what were the component? What were the component of a general steam power cycle? Steam power cycle. Tell me that. So there is a pump. This is all you already have studied. I'm just mentioning it. So we have a pump. We have a pump. We have a boiler. We have a boiler. We have a boiler. Then we are going to have a turbine. We are going to have this turbine, this steam turbine. So it is a steam cycle. So we are going to have a steam turbine. Then what we are going to have? We are going to have a condenser. We are going to have a condenser here. Okay, we are going to have a condenser here. From condenser, it will go to the pump. So let me write the state points. So let it be 1, let it be 2, let it be 3, and let it be 4. So this is what we have learned already, the basic power cycle, basic steam power cycle, which has the following components like pump, boiler, steam turbine, and condenser. Pump, boiler, steam turbine, and condenser. So if I draw the TS diagram here, now, see, we are covering the new syllabus. So those who are not aware of the Rankine cycle, might feel some problem. So that's why I am just briefly discussing it. Okay. So here we have state 1 before the pump and state 2 after the pump. So what pump will do in general? In general? So pump will increase the pressure. So let me make two pressure lines. Like this. And this is where the fluid is entering to the pump and it is compressed, or we can say its pressure is increased to this point. Let's say this is 2. From here, it will go in boiler. So what is boiler? Boiler is a constant pressure. What is it? It is a constant pressure heat addition device. It is constant pressure heat addition. Okay. What is happening inside the boiler? Inside the boiler at constant pressure, heat is getting added. So we reach to this point 3, we reach to this point 3, and point 3 is the entry to the turbine. Point 3 is the entry to the turbine. So you might be aware that in turbine, what happened? We expand. It is an expansion device. We expand. So generally, we believe that it is isentropic. So it is isentropic expansion. This is the general assumption we make. This is the general assumption we make. So this is the isentropic expansion from 3 to 4. Now we reach the point 4, means the steam has exited from the turbine, and then it enters the condenser. So what do condenser do? Condenser is a constant pressure heat rejection device. It is a constant pressure what? It is a constant pressure heat rejection device. Okay, constant pressure heat rejection device. So Ganesh, you are asking, sir, please tell us how to get maximum score on this topic. So I will suggest just follow all the lectures what we are going to teach here. You will be knowing everything about this topic by the end of this series. And then if our questions come, I am sure that you will get your full marks from it. That's why this is the only way you get your full marks. See, I tell you all one thing. See, there are no shortcuts. In getting the rank in GATE. If you study well, you study from the right sources, you will definitely get through. Otherwise, there is no shortcut. Some people are briefing, like there are so many babas in this GATE industries. Like they will guide you in many ways. Like do this, you will get this, you will that this. That is all. You study the right thing without wasting your time. You will get through. Okay. So the purpose of this video or this series is, without wasting your time, just to giving you the technical content what is required as per the GATE expect, and what could be asked. Okay, so for that we are making some introduction. As okay. So in turbine, what is happening? Isentropic expansion is happening, and in condenser, constant pressure heat rejection is happening. So ultimately, from the first law of thermodynamics, we all are aware of the first law of thermodynamics. So is it in the GATE syllabus previously or not? So yes, it was in the GATE syllabus previously or not? It was in the GATE syllabus previously as well. Yes or no? So first law of thermodynamics. What first law of thermodynamics telling us? That the net work from a cycle is heat added minus heat rejected. Okay, I'm briefly describing what you are knowing till now. Okay, so what first law suggests us that if there is heat addition, there is heat rejection, we will have some network. We will have some work done. We will have some network out of this whole system, out of this whole cycle. Okay, then by using or by multiplying power to it, if you want to know the power, you can multiply the m dot from the work net, when work net found here was in unit of kilojoule per kg. Generally, kilojoule per kg unit we derive. So power m dot is equal to work net. So m dot is what? Kg per second. So we will get something in kilowatt that we call in general the power. Now, from the second law of thermodynamics, what we do? We find the efficiency. We will say, sir, we will have work net, and we divide it by heat added, means output upon input, and we will have the thermal efficiency. Of this cycle. We will have the thermal efficiency of the cycle, isn't it? This is what you people are doing till now. Yes or no? This is what you people are doing till now. Yes or no? Tell me. Those who are live. Ganesh, Gani, you are asking me, please tell us how to solve problems on first law of thermodynamics, my dear friend. This is the lecture not for this purpose. Okay, the purpose of this lecture is to cover the new part in the GATE syllabus. The new part in the GATE syllabus. So at the GATE Academy channel, you will find the videos on the thermodynamics. There you will find how to use the first law. But the purpose of this topic, this lecture series is not that. It's not that. We are here to cover the new syllabus only. Okay. Although in this new syllabus, wherever the first law is applied, wherever first law is applied, we will see it. Wherever first law is applied, we will see it. Okay. Okay. So here we have a steam turbine. From this syllabus, since it is added in GATE 2021, that's why in previous year GATE papers, you won't find problems from this topic, what we are going to discuss. So we will do the problems in the class itself, in here itself, no problem. Okay. So this was our cycle. This was our cycle. Now tell me one by one. See, let me tell you, the purpose of this video is to teach you the new syllabus in GATE examination, not the existing syllabus. Okay. We are claiming, we have given the title to this video as the new syllabus that has been added in GATE 2021 examination. Okay. So it won't be right to keep on discussing what was already there. Okay. So we are here trying to cover which was not already there in GATE examination, So let's see again. But trust me, you will come to learn everything. Okay. So that's why I am briefly explaining all this to you. Okay. So we have this. Now, as I have mentioned, from boiler, we have some heat addition. At condenser, we have some heat rejection. So out of this cycle, what we are getting? In this cycle, what we are giving? We are burning some fuel. We are giving some input. Okay. We are giving some input to this cycle. So mostly it is in the form of burning of fuel. Okay. So heat is getting added in the boiler. And if I see the system as a whole, our work net, we are getting some work net out of this cycle. And this work net, when converted to power, is going to where? Is going to some generator. Where this mechanical energy is getting converted into electrical energy, where the mechanical energy is going to convert it into electrical energy. As Amesh, you have mentioned, efficiency is equal to shaft work upon heat supply. That is mechanical efficiency. Okay, that is overall efficiency. Okay, so this is work net. If this work net if this work net will go to the generator will create some electrical power. Okay, electricity. So this generator is the part of electrical engineers. Electrical engineer will take care of the generator. We have to take care about this. So from the first law, what we can say, now listen to me very, very carefully, you will get the concept. From first law, what we can say, that if we are providing some input in the form of heat addition, we cannot 100% utilize that input. So some part will be rejected, So we have added something, we have rejected something. So our network is coming out. Network is coming out of the system, which is further transmitted to the generator, and generator electricity will be generated. Electricity, what is the purpose of this power plants? Electricity will be generated. Yes or no? What is the purpose of the power plants? To create electricity. Yes or no? So electricity will be generated. So from this part, generator part, electrical engineers will take care. Electrical engineers will take care of the generator part. Being mechanical engineer, what we have to take care about? We have to take care that we must transmit the mechanical work to the generator. Say yes or no. Those who are live are able to understand this fact or not? Or not. So this is what we were studying before as well. This is what we were studying before as well. How we were studying all this. So let me briefly describe that also. So how we were doing all this. How we were doing all this previously. How we were doing all this previously. So we were preparing a TS diagram. Like this, as I have prepared earlier as well. We were preparing a TS diagram. So this is 1. This is our 1. This is our 2. This is our 2. This is our 3. This is our 3. And this was our 4. This was our 4. Right? So by using a chapter in thermodynamics named Properties of Pure Substances, this was already there in the previous GATE syllabus. Properties of Pure Substances. Heard the name of it? Properties of Pure Substances. So from there we get the idea how to calculate enthalpy of 3 point, enthalpy of 4 point, enthalpy of 1 point, enthalpy of 2 point, So what is the work generated by the turbine? The turbine work was said to be H3 minus H4. The pump work was H2 minus H1. Our heat added was H3 minus H2. Our heat rejected was H4 minus H1. So from properties of pure substances and the analysis of Rankine cycle, we were doing that, and hereby finding the efficiency and all. Now listen to me. What has changed now? So till now, in the previous GATE syllabus, what we were seeing till now in the previous GATE syllabus, we were seeing broadly that this is a cycle. From this cycle, this is a pump, this is a boiler, this is a turbine, this is a condenser. So we were not bothered that how in pump the pressure is being raised. We were not analyzing pump as a device previously. We were not analyzing boiler as a device previously. We just knew that steam enters the boiler and comes out at high temperature, high pressure, and in superheated state. Say yes or no. This was our existing knowledge. That's after pump, the steam enters, the liquid enters the boiler. After pump, the water enters the boiler and heat is added to it. So it gets converted into steam by virtue of the heat energy, heat supplied by the burning of fluid. So it changed into high temperature, high pressure steam in the boiler. So we were not unfolding the boiler till now. That what exactly is happening in the boiler. What are the constituents of the boiler? We never seen till now, and we are not going to see that also in that video, because this year the boiler is not added in the GATE examination. Okay, so same way, broadly what we were knowing till now, before this addition, till now we are knowing this, that some high temperature, high pressure steam is entering the steam turbine and coming out in the form of like a mixture of water and vapor, in the form of wet reason, as we have seen in the TS diagram, and a work is generated and work is created. Say yes or no. This is what our existing knowledge is. Yes or no. From is at the entry to steam turbine, after boiler, some steam, high temperature, high pressure steam is entering the steam turbine and coming out. So what we knew already, we have information about this, we had information about this, and we had that, sir, our net work is coming out to be H3 minus H4, and I am neglecting the pump work here because the pump work is very, very less. This is the assumption what we make in a Rankine cycle while we study Rankine cycle. Say yes or no. Is it true or not? Is it true or not? So till now what we knew that some steam is entering the steam turbine, some steam is exiting the steam turbine and then entering the condenser, and meanwhile we are getting some work out of it. Out of it. So what has been added in the GATE syllabus? Now we are expected to analyze, unfold what is happening inside this box. And we are getting some work out of it. So this is 3, this is 4, this is 3, and this is 4. So when steam enters at state 3 into turbine and steam exit at state 4 into the turbine, we get some work from the turbine. That is H3 minus H4. So till now we knew this is happening. Now the question is, this will happen. This is happening. But now the question is that how it is happening. The question is now how this is happening. Okay, this is what is added in the GATE syllabus. Till now we knew that this is there. Till now we knew that if some steam is entering to the turbine and exiting from it, we are getting some work. We are getting some work out of this turbine. Ganesh, I have scored 77 marks in GATE examination in mechanical branch. Okay. So WT is H3 minus H4. W3 is H3 minus H4. So till now what we knew that if the steam enters the steam turbine and comes out from it, we will get some work from the turbine. Now the question is how. So this is the new addition to GATE examination. Okay. This is the new addition to the GATE 2021 syllabus. That's how this turbine work we are achieving. How this turbine work we are achieving here. How this turbine work we are going to achieve from here. Okay. So is it clear that what is the new syllabus about a steam turbine? Rankine cycle was already there. First law of thermodynamics, second law of thermodynamics, entropy analysis was already there. This much was already there, that we have a boiler, steam turbine, condenser. We will see multiple cases like reheating, okay, like reheating and everything. Reheating is there. Open feed water heaters are there. Closed feed water heaters are there. The performance of Rankine cycle parameters were there. So these things were already there in GATE syllabus. So what is the new addition to the GATE syllabus? So the new addition to the GATE syllabus is that how this steam turbine is creating some work, some useful work. How this steam turbine is creating some useful work. So we need to unfold this now. We need to understand this. We need to unfold this now. Okay. We need to do what? We need to unfold this, that how a steam turbine is going to create some work. How the steam turbine is going to create some work. And definitely, if I name this calculator as steam turbine, and transfer and add some steam to it and send some high temperature steam to it, it won't convert it into useful mechanical work, would it? Let me name this calculator as steam turbine. So naming something as steam turbine won't do it. There has to be something inside the steam turbine, inside this big box, which is helping us. So what is inside this big box of a steam turbine? we are going to analyze here that how this steam turbine is going to convert the high temperature, convert the heat energy of high temperature, high pressure steam into some useful work, So let me firstly define the steam turbine. So in this lecture series, what we'll do, we will unfold this steam turbine. That what is happening inside this box, that we are getting this work out of it. We are getting this work from it. Okay. So now if I define the steam turbine, So what we have learned till now, that in a steam turbine, the steam is entering at a high temperature and high pressure. So let me define the steam turbine on the basis of your existing knowledge. So steam turbine, it is a prime mover, we can say. It is a prime mover here. From here onwards, actually, we have begun with the new syllabus. So it is a prime mover. Which convert heat energy of high temperature, and high pressure steam, which convert heat energy of high temperature and high pressure steam into useful mechanical work. It is into useful mechanical work. So this information we have obtained even from the existing knowledge we have of the steam turbine or Rankine cycle or steam power cycle. Say yes or no. This definition is understood or not? Those who are live, I am expecting the interaction from them. Okay. So what further about it? So this is we already knew. So I am giving you a new information that steam turbines are axial flow devices. These are what? These are axial flow devices. What do you mean by axial flow devices? What do we mean here? This is the spice of an objective question as well. From here, an objective question of 1 mark theory question can arrive that steam turbines are what kind of devices? So these are axial flow devices. So what do we mean by axial flow devices? So axial flow means what do we mean by axial flow devices? So axial flow means that steam is flowing. Yes, you are right, Shahrukh Khan. Okay, so steam is flowing in direction parallel to the axis of rotation. Okay. Now what else? These two things, is it clear? These two things is clear about steam turbines. Firstly, what we already knew that in steam turbines, high temperature, high pressure steam is entering. And then it will be converted into some useful mechanical work. Which further will send to the generator part, and that will take care by electrical people. So our work as a mechanical engineer is to create mechanical work out of the cycle, and steam turbine is the component at which this work is getting created. Okay, so first part of the definition. Second part, that what kind of a devices they are, what kind of devices they are. So they are axial flow devices. They are what? They are axial flow devices. Now what else? What else? Now, as I said that we are going to unfold this steam turbine. So till now, what we were knowing, that sir, this is a steam turbine. This is a steam turbine. So as I said, now we have to understand what is happening inside it. What is happening inside it? So let me unfold it. Let me unfold it to some extent. To some extent. So now I will say, so what we were seeing a steam turbine. We were seeing a steam turbine. Now I will say it is a combination of nozzle. It is a combination of nozzle and a moving blade. It is a combination of nozzle and moving blades. It is a combination of what? It is a combination of nozzle and moving blades. So now what we were saying that something at three state point, our steam is entering into the steam turbine and coming out at state 4, and in this duration, our some network is getting created. Now what we will say now? From now we will say, due to this new addition in gate syllabus, what we'll say that now, instead of saying that the steam is entering the steam turbine, now we will say the steam is entering into the nozzle. When it exits from the nozzle, it will go to the moving blade. And we will have some work generated with us. We will have the work generated with us. Okay. Now some people will say here, sir, we have heard in reaction turbine there is no nozzle, there is fixed blade. So please have patience. When that right time will come, I will definitely tell you. Okay. For now, fixed blade also the velocity is getting increased. So we can name it nozzle as well. No problem at all in that. But when the time will come, I will tell you that. When the time will come, I will certainly tell you that. What is the difference? Okay. So now, how we can say the things, how the things are changing, you are getting or not? How the things are changing. Okay. Now, in Rankine cycle, in previous gate syllabus, what we were seeing that this is entering into a steam turbine. This is entering the steam turbine at this state. It is exiting from the steam turbine at this state, and we are getting some work out of it. Now, what we'll say that steam turbine is the assemblage of. Now, let's make some English out of it. What we have seen, let's make some English out of it. So, steam turbine is what? Steam turbine is a assemblage of. In steam turbine is the assemblage of nozzle and moving blades. Would it be right to say steam turbine is the assemblage of nozzle and moving blade? Yes or no? A steam turbine is the assemblage of nozzle and moving blade. Okay. A steam turbine is an assemblage of nozzle and moving blade. Okay. Would it be right to say so? Yes or no? Would it be right to say so? Yes or no? Okay. As we have seen, you have to respond on the chat. You have to respond. Now tell me, is it right to say steam turbine is an assemblage of nozzle and moving blade? No, moving blades are not compressor. Compressor and turbine depends upon that what we are getting out of it. Okay. So a steam turbine is an assemblage of nozzle and moving blade. Okay, nozzle and moving blade. Now, can you guess how our syllabus will proceed? How this lecture series will proceed? So this series will proceed as I have unfolded steam turbine into nozzle and moving blade. So later in the series, what we are going to do, we are going to unfold the nozzle first. We are going to unfold the nozzles first, Then we are going to unfold the moving blades. That what are the kind of moving blades and what are the different condition in that is guide blades are called fixed blades there. That is there in reaction turbine. At fixed blades or guide blades, there is also increase of velocity. So you can for time being call them nozzle. No problem in that. Understood? Understood? Okay. So a steam turbine is nothing but an assemblage of nozzle and moving blades. So in this series, what we are going to do, first we are going to analyze the nozzle. We are going to have understanding about the compressible flow. It is also one new thing added into the GATE syllabus. So understanding the nozzle, we must understand the compressible flow also. Okay, so briefly in 2 lectures, I will explain you how nozzle does work in different conditions and what are the outcome of it with respect to the thermodynamics, or power plant. Okay, then further we will go and analyze the moving blades, that what is the geometry of the moving blade, how it is creating the work and how it is going to operate. Okay, so for now we can say steam turbine is an assemblage of nozzle and moving blade. So what happened broadly in nozzle? Let me say what happened broadly. What happened in nozzle? So in nozzle, what broadly happened is the velocity increases. I hope you all are aware what nozzle is, what happened broadly in nozzle. So velocity increases and pressure decreases. If in some geometry, if we are flowing the fluid from something and velocity while flowing through it increases and pressure while flowing through it decreases, can we name it as a nozzle? Yes or no? Can we say it as a nozzle? Yes or no? So here in the steam turbine, what broadly happening in nozzle? Steam expands, and you know expansion means pressure decreases. Expansion means what? Pressure will be reduced. So in nozzle, steam expand first, speed expand first, and then with high velocity, enters the moving blade. Okay, so firstly now see unfolding is taking place now from 3, the steam turbine, where what in previous paper what we were seeing, that at 3 it's just entering the steam turbine and some work is getting created. Now what we are going to see, what we are seeing in which way, that now it will first enter into the nozzle, where expansion of steam will take place, so its velocity, its pressure decreases, its velocity will increase, and then it will go to the moving blade. So now broadly what happens in a moving blade? Why I'm using this word broadly? Because we are going to see in depth that how this all is happening. But broadly what is happening in, as till now we knew broadly what is happening in a steam turbine. Now we are seeing what is broadly happening in nozzle and what is broadly happening is moving blade. So what is broadly happening in moving blades? So we can say what? After coming out from the nozzle, the steam is having very high velocity. Yes or no? Now you have to tell me yes or no. Steam is having very high velocity? Steam is having very high velocity. Say yes or no? Yes, sir. It is having very high velocity before entering to the moving blade. Now tell me, if something enters with a very high velocities into the blades, it will definitely strike the blade at high velocity. Yes or no? Yes or no? So in the moving blade, what is happening? High velocity steam is striking, high velocity stream is striking the blades. High velocity steam is going to strike the moving blades, is going to strike the moving blades. Okay. So when striking will happen, what will happen? The steam or the stream of the steam will get deflected. Yes or no? High velocity steam will strike the moving blades. So after the striking, what will happen? The steam will get deflected. And when this deflection takes place, when the steam get deflected, there will be some loss of momentum. Yes or no? There will be some loss of momentum. And as told to us by Newton, whenever loss of momentum is there, whenever loss of momentum is there, what will happen? Some energy, some torque will be stored. In the wheel on which the blade is mounted. So what will happen? This loss of momentum is going to get stored. This momentum is absorbed or is stored by the rotating wheel. By the rotating wheel on which the blades are mounted. And hence torque will be created. And this torque will rotate the shaft, and that shaft will go inside the generator, and electricity will be generated. So what broadly happens in steam turbine? That we are getting some work out of it. Now what we have just distributed the whole steam turbine into two parts. So a steam turbine majorly built up of nozzle and moving blade. So in nozzle, what broadly is happening? That the steam coming out of the boiler getting expanded. So so its velocity is getting increased, its pressure is getting decreased. So before entering to the moving blade, the velocity of the steam is very, very high. So when it goes to the moving blade, it is going to definitely strike the blade. So when it is going to strike the blade, it will get deflected. Due to that strike. So because of that deflection, the loss of momentum is there. You can call it the change of momentum. What Newton law says us, that whenever there is a change of momentum, a force is generated. So this is a rotational system. This is an angular system. So we are talking about the angular momentum. So due to this loss of momentum, this angular momentum will be conserved. And hence the torque will be created. And this torque will be further transmitted to the generator, where we are going to create the electricity. Is that clear or not? Till now, is that clear or not? What is broadly happening in the moving blade, and what is broadly happening in the nozzles? Say yes or no. can say yes or no. You can say yes or no. Okay. Okay. So till now everything is clear. Till now everything is clear. What is broadly happening? What is broadly happening in a steam turbine? What is broadly happening in a steam turbine? Okay. All right. All right. Okay. So what you have to do now, please subscribe the Gate Academy English channel as well as Hindi channel. Okay. So you will get to know everything of this new Gate syllabus. The new notification will come on the channel about the next lecture. So today the next lecture is at 1 o'clock. From 1 to 3, we are going to see the next part of it. Okay. So till now, if everything is clear, let me write some applications of a steam turbine. These all things can be asked in 1 number theory question in GATE examination, in 1 number theory objective question in GATE examination. So can you suggest me some applications? So the application of a steam turbine is in power generation. Power generation. Yes or no? Yes or no? Obviously in power generation. Apart from this power generation, it is used in large equipments like ships, submarines, submarines, okay, ships, submarines, to propel them, okay, to propel them. Propel means what? Propulsion, what you call, to propel them, okay. So these steam turbines find this application in the large ships, submarines as well, where we need some power, high amount of power to do the propulsion of it, Also these are used to run large equipments, like in aircraft we do not use it. Shahrukh, because steam is created with water, so it is high in weight. So in aeroplane we are using gas turbine cycles. So that the weight of the system, the inertia of the whole system is less. So to run the large progenories, we have mentioned this power generation as power generation, what you are saying. So run large equipments like compressor, big compressors, big compressors, or any big power consuming device like blower, pump, etc. Okay. So got the applications of steam turbine? Yes or no? Say yes or no. Sir, steam turbine is nothing but we are discussing the steam engine only. You can say, because it is creating some power. Okay. So now we have some brief introduction about the steam turbine. We have understood what we are going to study in this lecture series. We are going to study about the nozzles first. We will understand how the nozzle works. We will do some problems on it. Okay. After the nozzle, we will go to the turbine part, the moving blade part. Okay, the moving blade part. There we will see the impulse reaction turbine, their compounding and everything. Okay, then we'll move to the gas turbine thing. So firstly, let us focus about steam turbine. So now the time has come to do the classification, of steam turbine. So we will have a brief introduction about the kind of steam turbines that we are going to study or which are in use in thermodynamics or power plants. Okay. So steam turbines can be classified based upon their working principle, based upon their working principle. This is the first classification, based upon the working principle. based upon the working principle. So based upon the working principle, we can classify steam turbines into impulse turbine, and reaction turbine, impulse turbine and reaction turbine. Okay, so on the basis of working principle, there are two kind of turbine we can classify into. That is steam impulse and reaction. That is impulse and reaction turbine, impulse turbine and reaction turbine. Okay, so what is the basic difference between impulse turbine and reaction turbine? On the basis of their working principle, is let us see. So impulse turbine. First let us talk about the impulse turbine. Okay. So impulse turbine, what happens in the impulse turbine? Impulse turbine, as I said, is a combination of nozzle and moving blade. It's a combination of nozzle and moving blades. Okay, nozzle and moving blades. So let's say we have to focus upon two things. Here. One is pressure and other is velocity. So let's say we are seeing the pressure here, we are seeing the velocity here. So what is the entry point? To the nozzle? So entry point to the nozzle is, let's say, O. At O, there will be high pressure and high temperature, yes or no? How I am saying there will be high pressure and high temperature? Because we have this TS diagram that we already knew. See this TS diagram on the screen. So here at the entry to the nozzle, the temperature and the pressure of steam is very high. We can see this from the TS diagram. Okay. Now come here. So high pressure steam is going to enter into the nozzle. And in nozzle, what we have understood by the definition, that in the nozzle, expansion will take place. What will happen in the nozzle? Expansion will take place. In the nozzle, what will happen? Expansion will take place. What will happen, my friend? Expansion will take place. So expansion will take place means what? That the pressure reduces while the steam flows in the nozzle. Okay, so our pressure goes on decreasing, and it reaches this value P1, and you can clearly see that P1 is less than P0. What is here? P1 is less than P0. Okay. Now, what will happen in impulse turbine? When this steam goes into the moving blade? So when this steam goes into the moving blade, the pressure remains constant. The pressure will remain what? Pressure will remain constant. So what happens in the impulse turbine? Now, as I said, I'm unfolding it even further. We have seen the steam turbine is a combination of nozzle and moving blade. Now we are seeing what is happening in impulse turbine and what is happening in reaction turbine. Okay. So in nozzle, what is happening? The pressure goes on decreasing. of the steam while it flows into the nozzle, and it will reach a value P1. So this is the minimum pressure that can be attained. From the nozzle. Now the question is, sir, how we will know this minimum pressure? So for that, we have to analyze the nozzle. Okay, so we will do that. That what is this pressure till which the expansion can be done. Because being an engineer, I always tell my students that the religion of a student is to extract whatever we are getting. Okay, our religion is to get as much as we can, okay, and give as less as we can. Take more, give less. We have to take more and we have to give less. Okay, so if there is something energy is left in the steam, we have to utilize every single part, every single portion of energy that is available with us, in the steam. Say yes or no. Say yes or no. Okay. So we are what in nozzle, what is happening? The pressure is reducing, the expansion is taking place, and from this point in moving blade, when this steam goes in the moving blade, the pressure remains constant. The pressure remains constant. So what happens to the velocity? What will happen to the velocity? So velocity, let's say at entry, that let's say at entry into the nozzle, the velocity is V naught. The velocity is V naught. Now, as it flows into the nozzle, the velocity increases. As it flows into the nozzle, the velocity increases, and it reaches the value V1. It reaches the value V1. So V1 is certainly greater than V naught. V1 is certainly greater than V naught. Okay. Okay. Now, as this high velocity, here you can see that the steam is having very high velocity, or we can say in impulse turbine has the highest velocity. V1 is what? Highest velocity that can be attained, while expanding the steam into the nozzle. So at this one point, our steam having very high velocity is going to enter the moving blade. So very high velocity, or I can say with very high kinetic energy. I can say like that also, very high kinetic energy, because you know the kinetic energy is half mv square. So higher the velocity, definitely higher the kinetic energy. So at the exit of nozzle, our steam is having very high velocity, very high kinetic energy, and now it is going to enter into the moving blades. So as it is entering the moving blade, what will happen? What will happen? There will be loss of momentum. So when this high velocity steam is going to strike the moving blade, and as the blade is moving, it is giving in a way its energy to the blade. So when it is giving its energy to the blade, its energy goes on reducing. Okay, the loss of momentum will be there. The loss of momentum, as we have mentioned it earlier, loss of momentum will be there. So when loss of momentum will be there, the velocity goes on decreasing. And this velocity will try to approach the initial velocity at which the steam enters the nozzle. So overall, what is happening in the impulse turbine? I am making this for impulse turbine. So what is happening? High temperature, high pressure. Steam enters the nozzle, and in the nozzle, the pressure goes on decreasing. The velocity goes on decreasing, and at the exit to the nozzle, the pressure is reduced to its minimum, and the velocity is increased to its maximum. So here we can say P1 is minimum. We can say P1 is minimum possible. V1 is maximum possible. Yes or no? So in impulse turbine, in nozzle, we are reducing all the pressure. And what about velocity? We are increasing all the velocity. So what will happen? In nozzle, pressure decreases from maximum to minimum. In the nozzle, the velocity increases from minimum to maximum. So Virender, you are asking, sir, can V2 goes less than V0 at exit? So it is not likely. It is not likely. If it goes below V0, it is only good for us. But as you see, the pressure is very much related with the pressure as well. Okay. So sometimes what happens, if the velocity goes below a certain value, will go below the certain value, pressure may reduce from the atmospheric value and will become vacuum. So in that cases, back pressure will take place, backflow will take place. So that is undesirable condition. So although I have written V2 is approaching to V0, so in actual practice, this V2 never even reached to V0, or I can say not generally reached to the V0, not generally reached to the V0. Okay, is that clear? So what is happening in impulse turbine? In nozzle, we are reducing all the pressure energy. In nozzle, we are increasing all the pressure, all the kinetic energy. Is that clear or not? Is that clear or not? Is that clear or not? Yes or no? Yes or no? Yes or no? So now, as you see in moving blades, in impulse turbine, as you see in moving blades, so let me write the key points here. Let me write the key points here about impulse turbine. So in nozzle, pressure decreases. In nozzle, pressure decreases, velocity increases. In impulse turbine, in nozzle, pressure decreases, velocity increases, and after nozzle, or at exit to the nozzle, or before entering to the moving blade, whatever English we want to use, we can use. At exit of nozzle, the velocity is maximum and the pressure is minimum. So what we can say? Before, in other words, what we can say, before entering to the moving blade, all pressure energy of the steam, is converted to before enter to moving blade, all pressure energy of the steam is converted to the kinetic energy. Okay, so we can again say, so this is just a play of English. If we have understood the concept, we can write it in many ways, and again it can be asked in many ways. But this all is just a play of English, nothing else. The concept will be same. Okay, so we can write like this also: before entering to moving blade, all the pressure energy of steam is converted to kinetic energy. So steam enters the moving blade with highest velocity and kinetic energy. So steam enters the moving blade with highest velocity and kinetic energy, which gets converted into the torque of the rotating wheel, Okay, so you can see in the moving blade, this is very important point. In the moving blade, the pressure of the steam is constant. In the moving blade, the pressure of steam is constant. Okay. So now this is important. Now this is important. Now listen to me. Listen to me. So here comes a question. Here comes a question that why? Why the in moving blade the pressure do not change? Why in moving blade of impulse turbine pressure do not change? So why is it so? Is it so because of the geometry? Is it so because of the geometry of the blade of impulse turbines? The geometry of the blade of impulse turbine. So how is the geometry of impulse turbine blade? This is symmetrical. This is symmetrical. So those who are live or seeing this video, this is the spices for objective papers. Okay. So why pressure do not change while flowing into the moving blades of the impulse turbine? Because those blades are symmetrical. Those blades are symmetrical, or you can say passage. You can say what? You can say the passage between the two blades. The passage between the two blades is constant. The passage between the two blades is constant. Is what? Is constant. So since the passage is constant between the moving blades, between the two blades of impulse turbine, pressure do not change. Pressure do not change. So someone will say, so how the velocity will change? So velocity is changing because of the striking, because of the loss of momentum here, because of the loss of momentum here. So why, if someone will ask you why in the moving blade pressure of steam is constant? Because geometry, because of the geometry of the blade which is symmetrical, because of the geometry of the blade which is symmetrical. So somewhat a impulse turbine moving blade looks like this. Somewhat impulse turbine moving blade look like this. This is symmetrical. This is symmetrical. So what you are saying, Tojan? Sir, to prevent losses in blade, the pressure is kept constant. No. Losses will be there. See, whatever losses are going to happen, that are going to happen. But see, why we are making this shape? Because this is somewhat, if you have to make this shape, so this is less costly. This is less costly. Firstly, it is easy to manufacture. It is easy to manufacture. So there will be greater losses here as compared to reaction turbine. In impulse turbine, the losses will be greater. The work done, the work created will be lesser in the impulse turbine. But why in some cases we are preferring it? Because of the cost, the manufacturing factor. So for low power generation, we generally use this impulse turbine. For low power generation, we generally use this impulse turbine. Is that clear? Is that clear? Okay. Okay. So it is not about the losses. It is about the application. It is about the application. As you all can understand this, that sometimes cost is important, sometimes quantity is important. Okay. So reaction turbines are generally used where high power requirements are there, where the power requirements are higher, and impulse turbines are used where the power requirements are lesser. Okay. So this is about the cost and the application. Okay. So why? So again, coming back to the point, in the moving blade, the pressure of steam is constant. It so happens because the geometry of the blades of impulse turbine is kept constant. Is kept symmetrical. Is kept symmetrical. Now a little bit of reaction turbine. We will firmly unfold the impulse turbine, but in this lecture we are just seeing what we are going to study and the introduction part. So reaction turbine. What happens in reaction turbine? What happens in reaction turbine? So firstly, let me tell you, I was discussing about the blade. So the blade is not symmetrical. The blade geometry. Let me talk about the blade geometry. So blade geometry. So blade is non-symmetrical. Blade is non-symmetrical. The blade is not symmetrical. Okay, the blade is going to be non-symmetrical and is generally of airfoil shape. It's generally of airfoil shape like this. Generally of airfoil shape. Okay, so since Since it is not symmetrical, it is having a airfoil shape. It is having a airfoil shape. The pressure while moving through the moving blade of the reaction turbine goes on decreasing, and it is not constant. It is not constant. So let us see how this thing is happening. Let us see how this thing is happening. Let us see how this thing is happening. So let's see. Let's see. So we are talking about the reaction turbine. We are talking about the reaction turbine. We are talking about the reaction turbine. So we have some fixed blades here. We have some fixed blade here, which we sometimes call nozzle. There is no problem calling it a nozzle also, because in this also the velocity increases and the pressure decreases. The velocity increases and the pressure decreases. So there is a fixed blade, there is a moving blade. There is a fixed blade, there is a moving blade. So what will happen? What will happen? What will happen? So what was happening? What was happening in impulse turbine? What was happening in impulse turbine? In impulse turbine, the complete pressure energy of the incoming steam, was getting converted in the nozzle itself, But here in reaction turbine, what happens? The steam enters. Let's say the steam enters at high pressure P0. Okay. So while flowing into the fixed blade thing, this pressure will decrease. But at the end of the fixed blade, the complete pressure energy is not expended. Means still at this point. See, now compare with impulse turbine. At this point, there was no pressure energy. Left in the steam to get further expanded, to get further used. But here in the reaction turbine, what is happening at point one? Not all the pressure energy has been converted. So at point one, we still have the pressure energy left with us. Which further get reduced, which further decreases in the moving blade. Okay. So here in reaction turbine, what is happening? The pressure reduces in the fixed blade as well as the moving blade also. The pressure decreases in fixed blade as well as the moving blade. Now what will happen to the velocity? So in the fixed blade, which is acting as a nozzle, you can see in fixed blade, which is acting as a nozzle, velocity increases as similar to what we have seen in the impulse turbine thing. But this is not the maximum velocity. Till the steam can reach to. Okay, because the pressure energy, see, the steam is still having some pressure energy. The steam is still having some pressure energy. From this point, from one point, when the steam enters the moving blade, pressure and velocity both will be decreasing. So as in the moving blade, the striking will take place, the loss of momentum will take place, because ultimately we have to rotate the wheel. So in order to rotate the wheel, we have to have the loss of momentum. Okay, so when the loss of momentum takes place in moving blade, the velocity certainly decreases. Okay, So here, what is the basic difference of reaction turbine and impulse turbine is at the entry to the moving blade, in impulse turbine, the complete pressure energy is already converted into kinetic energy. But in reaction turbine, at the entry to the moving blade, the steam is having both kinetic energy and pressure energy and they both get decreases in moving blade. So the pressure is not constant. The pressure is not constant in the moving blade region as well. So generally we use series of fixed blades and moving blades, six fixed blades and moving blades in in the reaction turbine. So let's say this is fixed blade 1, this is fixed blade 2, this is fixed blade, this is fixed blade 1, this is moving blade 1, this is fixed blade 1, this is moving blade 1. So still after the exit of steam at moving blade 1, steam might have some pressure energy left with it. Okay, what happens in impulse turbine? Once it is exit from the moving blade, it has lost all of its energy, either pressure energy or kinetic energy in general. Although there will be compounding of, we will see the compounding of impulse turbine. There we can see how to make such arrangements in which we use the combination of this nozzles and the blades. We use the combination of the nozzles and the blades. So that we are going to see in the compounding part. Okay, but for now we can certainly think that whatever pressure energy or kinetic energy, whatever pressure energy the steam was having in the nozzle of impulse turbine, all of the pressure energy got converted into the kinetic energy. But that is not the case in reaction turbine. So at the entry to the moving blade, it is having both kinetic and pressure energy, which further get decreases in the moving blade. So let's say at the end of moving blade, our turbine, our steam still is having some pressure energy. So what will happen in the first fixed blade? So pressure will further decreases, and velocity in fixed blade will increase further. So what is happening in fixed blade? Velocity increases, pressure decreases. So why the velocity is increasing? Why the velocity is increasing in fixed blade? Because in fixed blade, the pressure energy get converted into kinetic energy. As you know from the first law of thermodynamics, energy cannot be created, cannot be destroyed. It can be transformed from one form to another. Is that clear or not? Tell me. Now tell me what will happen. When this steam enters the moving blade. What will happen is when this steam enters the moving blade. So this pressure will further decreases. And velocity also decreases. In the moving blade. And moving blade is made to have rotated. It's made to have some rotation. Okay. So what is happening in reaction turbine? What is happening in reaction turbine? In fixed blade, what is happening? Pressure decreases, velocity increases. In moving blade, what is happening? Pressure again decreases, velocity also decreases. So in fixed blade, velocity increases in fixed blade. So in fixed blade, what is happening? It is acting as a nozzle in which pressure decreases, velocity increases, and in moving blade, it is working like in pressure reduces and velocity also reduces. Now someone will say, sir, is it working like a diffuser? So no, in diffuser, the velocity decreases and pressure also decreases. Pressure increases. So this is not happening. In moving blade, both pressure and velocity both are decreasing. Okay. So again, what is happening? Let us see this thing again. So in reaction turbine, the steam, high temperature, high pressure steam enters the fixed blade, whereas pressure decreases, velocity increases. Then in the moving blade, it goes in the moving blade where its pressure gets further reduces and velocity also reduces. Then again, if I apply one more series, a series when I say, so it means combination of fixed blade and moving blade. That we are going to see in later future classes. Okay. For now, we are seeing the basic differences, basic introduction of the steam turbine. Okay. Okay. So in the second set of fixed blade, again, what will happen? The velocity will increase, the pressure will decrease. The velocity will increase, the pressure will decrease. Okay. So at the exit of the second stage of the fixed blade, we will go again to the moving blade where pressure further reduces and velocity also reduces. So if we can use some more stages. A stage means a combination of fixed blade and moving blade. So we can apply even further series of fixed blade, moving blade, fixed blade, moving blade, and so on. And this thing will goes on happening. Whenever the steam flows on the fixed blade, its velocity increases, pressure decreases. Whenever it flows in the moving blade, its pressure will decrease and velocity will also decrease. So is that clear till this point? Everything is clear till this point? Say yes or no. Those who are live can respond. To me. Virender, we can see that. Up to how many stages we can apply, sir? We can see that. So see, as I told you earlier also, being an engineer, what is our duty? Here, V1 and V3 can be equal, may or may not be equal. So what is our duty? Our duty is to utilize every portion of energy we can utilize. So we will use these stages till we have exhausted. So our duty is to exhaust. All the energy from this steam. We won't let it have a smallest portion of the energy. This is our target. Okay. So for that we require to do the staging that we will see in the later classes. Okay. So I am assuming that we are clear till this point of discussion. Okay. If there is any doubt, you can ask me. The live students can ask me till now. Okay. Is it easy or not? See, some theory part is involved. We have to see it. Okay. This can be asked in 1 mark or 2 mark question. And as I said, this series is not of that type of series in which we give title of something and we start teaching something else. Okay. So here I am assuming your time is very, very important. So I am trying to make full utilization of your time. Okay. So we are giving whatever is necessary to you in this video and in this series. Okay. So if you are liking all this, please do subscribe. Do subscribe the Gate Academy. Okay. So that you will get the notification of the further videos. Okay. Will that be done? Okay. So now let's see the basic difference from here. Questions can be asked, and this topic was already there in ESC syllabus. This was already there. In GATE syllabus, it was not there, but in ESC syllabus, all the things were already there. Okay, so I am taking reference from the question. We are taking reference of the questions from the ESC objective. Thank you, Amish. Okay. So what is the basic difference between impulse and reaction? Some objective questions might be asked from this also, of this also. Okay. So in impulse, what we can say that the pressure drop takes place. After all this discussion, you will be able to understand it very, very quickly. Pressure drop takes place in nozzle only. Yes or no? In reaction turbine, this pressure drop take place take place in both fixed blade, in both fixed blade and moving blade, in both fixed blade and moving blade. Isn't it? Isn't it? Yes or no? In both fixed blade and moving blade. Pressure drop takes place in both fixed blade and moving blade. Okay? Okay? What else? What else? We have seen the profile of the blade in impulse turbine. Profile of blade is what? The profile of blade is symmetrical. The profile of blade is symmetrical. Okay? And here the profile of the blade is not symmetrical. Profile is, yes, compressor was there in gate examination, but it was already added. It was already added in gate examination. I think from gate 2016 it is there. Compressor is there from gate 2016. So we are not going to discuss. We are not going to discuss compressor here. We are not going to discuss compressor here. Okay. We are going to strictly. We are going to see the things which are from gate 2016 is labeled. All right. So profile of blade is not symmetrical. Is aerofoil. Is aerofoil. Okay. Is aerofoil. Understood? Is aerofoil. What else? What else differences can be there? What else differences can be there? Okay. So as I said, this is cheaper. So this is simple. This is cheaper. Okay. Or other words, you can say easy to manufacture, or whatever play you want to play with English, you can do. Whatever play you want to play with English, you can do. Okay. So this is not that simple. Airfoil design, every one of us is aware that this design is not that simple. It's not that simple. So we can say complicated design. So which one will have higher cost? Which one will have higher cost? Tell me that. Tell me that. So obviously higher cost will be there. It will be of high cost. Obviously it will be of low cost. It will be having low cost. Okay. Okay. What else? What else? So as I said, cross-sectional passage between blades is constant. Between blades is constant. That's why between moving blade, that's why cross-section passage between blade is constant. That's why the pressure remains constant in the moving blade of impulse turbine. So Madhusmita, you are asking me, is this cost justified? Yes, it is justified. How it is justified, I'll tell you. So now just listen to this, I'll tell you. So cross-section passage, yes. Sorry. This is low cost. My mistake. As impulse turbine is simple and cheaper, it is of low cost, and as reaction turbine is complicated, is obviously of high cost. My writing mistake. Okay, this is my mistake. I was saying that impulse turbine is of low cost and steam and reaction turbine is of high cost, but I wrote opposite of that. Okay. So this is a typographical error. Okay. Now correct it. Okay. Impulse turbine is having low cost, as I told earlier as well, and reaction turbine is having high cost, as I told earlier as well. So cross-sectional passage between blades is not constant. That's why is not constant. That's why the pressure changes. Pressure drop will be there. While steam flows in the moving blade part of reaction turbine. Okay. So last for now, that Power developed. The power developed is low. Power developed is obviously low. As I told, there will be more losses in here. Power developed is certainly low. Power developed is certainly low. Okay. And efficiency also is less. Efficiency also is less here. Here, power developed is more. Power developed is more. Power developed is more. So efficiency is also generally high. Efficiency is also generally high compared to the impulse turbine. So where we should prefer the impulse turbine? Where we should prefer the impulse turbine? Where the power requirements are less, Madhusmita. I am justifying the cost thing now. So where power developed is less, where power required is less, we may choose the impulse turbine as the cost is also less of impulse turbine. Okay. But where the power required is high, we generally prefer the reaction turbine. And since the power generated in a reaction turbine is high, it is more costly. Okay, understood? Understood the basic difference between impulse and reaction turbine? Impulse and reaction turbine. Yes or no? Yes or no? Tell me, yes or no? So low cost and low power requirements, we use impulse turbine, as Amish you are saying, and high power requirements, we require the reaction turbine. So generally people are aware of this classification, but there is another classification. This is the second classification. We can classify it in another way based upon the shaft orientation. Okay, so this is another classification from which some objective theory question may arise. Okay, may come based on the shaft orientation. So based on the shaft orientation, we have tandem compounded, we have this tandem compounded steam turbines, and we have cross compounded. So let's see what is tandem compounded. So when all the turbines, so we know there is a high pressure turbine, there can be intermediate pressure turbine, there can be intermediate pressure turbines. We see all this thing in general power plant. We have seen the reheating. We can see the reheating cycle. So in reheating cycle, what we do, we put a high pressure turbine, we put a low pressure turbine. And if reheating is being done in stages, we use intermediate pressure turbine. Okay. So I hope you guys are aware of this. Are you or not? Okay. So this is one low pressure turbine. This is one low pressure turbine. And this is our generator. So in tandem compounded steam turbine, we just have one rotor. On which all the turbines are getting connected, and we are having one generator. So everything is connected to one rotor. We call it as tandem compounded. Now focus here. Now you are seeing in this figure, some turbines I am making like in one go, and what does this mean? Now focus here. What does this mean? What does this mean? So this means we are having two flows, one in this direction, one is this direction. So if 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 we are having a low pressure turbine represented like this, so it means it has two flows in two direction. It has two flows in two direction. Yeah, or we can say it has two flow direction. It has two flow directions. Is that clear? Is that clear? Is that clear? Okay. So low pressure turbine, we decide the direction of flows on the basis of low pressure turbine. So it can be one flow, it can be two flow, it can be three flow, it can be four flow. So how will be the three flow low pressure turbine will look like? How will be the three flow low pressure turbine will look like? So here on the screen you can see a picture. Okay, a picture. So see on this at here you can see our double flow low pressure turbine. So it is looking like this. It is looking like this. Yes or no? It is looking like this. So this is the representation of double flow. This is the representation of double flow. Here you can see a single flow low pressure turbine. A single flow low pressure turbine. So a single flow and a double flow combined, they will call as a triple flow. This is a representation of three flow direction, triple flow. This is a combination of three flow direction, that is triple flow. How I am doing that? You can see there is a double flow low pressure turbine represented like this. There is a single flow low pressure turbine represented like this. So how many directions are there? Three directions are here. Okay, here comes another figure. Here comes another figure. Okay, so here we are having two double flow low pressure turbines. Here one is a double flow low pressure turbine. Here another double flow low pressure turbine. So how many flows are there? What is the meaning by flow, sir? So it represents the direction. In the direction in which the steam may flow. It is the direction in which steam may flow. Okay. So here we have four flow directions. Here we have four flow directions. So first tell me by seeing these figures, can you recognize where there are two directions, where there are two direction of flow, where there are three direction of flow? Can you tell me that? Yes or no? Can you guys tell me those that? Yes or no? Yes or no? So if we have to represent six flow, we have to use three double flow low pressure turbines. We have to use three double flow low pressure turbines, right? If we have to represent five flows, we will use two double flow low pressure turbine and one single flow low pressure turbine. And this is how we give a specification. This is how we will give the specification to the turbine. How we will give the specification to the turbines? So TC represent tandem compounded. So first two words will represent the compounding. Either it is tandem compounded or cross compounded. So next we are going to see the cross compounded. So cross compounded represent the CC, will be represented by CC. Second we will write the direction of flows. Second thing we will write the direction of flow. So here there are two flow direction. So there are two flow direction of the steam. So two flow direction of the steam. So we will write it as two flow, 2F. Okay. Virender, I will answer your query. Just please listen to what I'm saying right now. Okay. First understand this because this is very important for objective point of view. Okay. So we will call it as TC, tandem compounded, 2F, that is two flow. And what will I write here? So let's say I have write 18 here. What is 18 here? What is 18 here? So 18 gives the height of, now listen to me very, very carefully. This is very spicy for objective. From here, lot of objective question can be asked. So this 18 gives us height of last blade. Height of last blade. Height of the last blade in inches. Remember this. This is giving in inches. This is giving in inches. Okay, we are giving the height in inches. So this is the way. So this is height. Height is measured from the center of the rotor, So this is 18. This is 18 inches. So how we will specify this turbine? We will specify this turbine by like this. So TC 2F18. TC 2F18. So this first will represent what is either it is tandem compounded or cross compounded. This 2F will be the direction of flow, and this 18 will give you the height of the blade in inches. Height of the blade in inches. So what is tandem compounded gas steam turbines? What is tandem compounded steam turbines? So first thing, every turbine will be connected to a single rotor. Every turbine will be connected to a single rotor. Every turbine will be connected to a single generator. So what we are having? We are having how we can define this tandem compounded. So we have single rotor. And single generator. We have single rotor and single generator. In tandem compounded. So this kind of turbine generally used in India, in our nation. This kind of steam turbines are generally used. So they usually work at, this is also can be asked in objective papers. So this is generally work at 50 hertz frequency. So you know to change the frequency into RPM. So if you change it into the RPM, it will come out to be 3000 RPM. So generally the tandem compounded steam turbines work at 50 hertz frequency with a single generator and at 3000 RPM. Single generator and at 3000 RPM. So is that clear about tandem compounded? What is tandem compounded? And Virender, about the direction of flow, as I said, low pressure turbine two flow direction means that steam can flow in two different directions. Steam can flow two different directions. And what will be the outcome of this direction of flow? That we will see when we unfold it further. We haven't unfold it in that way that we able to understand what is the influence of this flow direction. So what just we are classifying, we are trying to understand this specification. So is that clear till this point or not? So tell me one thing, you are getting to learn new things or whatever you had already in GATE syllabus, we are discussing that only. Are you getting new things or not? Yes or no? Yes or no? Tell me. Your feedbacks are very important. Okay. So as we have titled this lecture series as new syllabus, so we are strictly following the new syllabus. Okay, strictly we are trying to follow the new syllabus only. Okay, new syllabus only. Okay. So please subscribe this channel. New things in perspective to GATE 21. Whatever already there is in a syllabus, I think you already have covered that and or will cover that. But at the GATE Academy, I hope we are doing this for the sake of the students who have already covered the most part of GATE syllabus and now waiting to cover this new syllabus. Because see, what is the difference when you go to study by yourself? If somebody will say that you won't be able to understand it by yourself, he is lying to you. There is nothing in the world that you cannot understand by going from the books. Otherwise, how will teachers like us will understand? So don't believe on these silly things. You can learn by yourself. The only difference will be created that we will make things a little bit easy and will reduce your effort. And you will understand the things in an easier way, whatever is relevant for you. This is the only difference. This is what difference we are trying to create here at the GATE Academy. So do subscribe. Okay, do subscribe the channel so you get the notification, and also share and like to your friends so they also can come in the next lectures and get the maximum advantage. Okay, so in cross compounded, we have two generators. We have two generators. We have two generators. So the arrangement I am making, it is somewhat like this. It is somewhat like this. A general arrangement I am making. So this is one generator. Thank you, Amish. So this is a generator. This is a generator. So now cross compounded means from this we have another line going of rotor. We have another rotor line. So two generators are there. Two generators are there. Pardon my skills of drawing. Pardon my skills of drawing. Okay. So this is our another turbine, low pressure turbine. Let's say this is low pressure turbine naming 1. This is low pressure turbine named 2. And here goes another generator, Here goes another generator. Here goes another generator. So what is happening in cross compounded, as you can see? What is happening in cross compounded, as you can see? We are having two generators. And there are two different lines of rotor. So this system is generally used in some richer countries, developed countries, where they have frequency of 60 hertz. 60 hertz bipolar. 60 hertz frequency they are using, and bipolar generator they are using. So in India, this is not very much common. In India, what we are using, tandem compounded, and in America, like countries, they are using, because we are Indians, right? So they are using this cross compounded thing with bipolar generator and having 60 hertz of frequency. So if you convert it in RPM, you will get 3600 RPM. Okay, you know how to convert now from hertz to RPM. So you just have to multiply 60 here. Okay, 60 here, you will get the RPM, and here 60 hertz is there. So you have to multiply 120 and divided by 2, because it's a bipolar generator. So we divide it by 2. This is already from the existing knowledge of the gate. So here comes 3600 RPM. Now, can you specify this for me? So certainly it is a cross compounded. And you see, we have two low pressure turbines, in which two flow direction we can see. So it is cross compounded with 4 flows. Sorry, Chen, I'm coming to your doubt. So CC and 4F, and what should I write here? So let's say if I write 30 here, so this must be 30. The height of the last stage blade in inches. So how do we specify? Specification, how we do? Specification, this can be asked in objective in 1 mark question. So what will we do? We will see the shaft orientation. In the place of first 2 will represent the shaft orientation, either tandem or cross compounded shaft orientation, either tandem or cross compounded. In the second, you will see the number of directions, and last one, the height of the blade, height of last stage blade in inches, height of last blade in inches. Remember this inches thing as well. Otherwise, your answer will be wrong. Inches. Okay. Okay. So see, Chen, you are asking, sir, please tell us what are the frequently asked questions from this topic asked in GATE. So, sir, as I'm saying, this is added in GATE 2021 syllabus. This is added in GATE 2021 syllabus. So, if it is new in the syllabus, how we will have the questions of it, which already been asked? So previously it was not in the syllabus. So questions are not asked from this in GATE examination, but it was in ESC examination. It was there in ESC examination. So in ESC examination, objective questions were asked from this topic. So we are taking reference of that and teaching you according to that. And you can check, see what you guys can do. You can check any standard book like PKNAN, very good book of power plant. You go for it, you check it, what is written there and what you are getting at the GATE Academy. Okay. Okay. So in this video series, as I said, we are going to cover completely in all respect the steam turbine and the gas turbine. Also, we will cover the compressible flow here. Also, compressible flow will be covered here again. Already I have covered in Hindi in the GATE Academy Hindi channel. Okay, we already have covered, but here also we are going to cover the compressible flow with respect to the power plant thing, with respect to the nozzle. Anand, this is a way of specifying. This is a way of specification. Okay, you are asking me, sir, why is the height only of the last blade important? So sir, in engineering, we try to standardize the thing. Try to standardize the thing by providing it some specification. Okay, so this is just a way of specifying. Okay, the way of specifying. Now let's say someone has chosen to specify. Someone has chosen to specify it from the last blade. Someone has chooses to specify it from the middle blade, or someone is chosen to specify from it some other blade, some other turbine blade. So what will happen? There will be no standardization and you will not be able to understand anything. As you are going to purchase something in market, you see there is some standard they are following. That this is ISO 111. For example, ISO, this product is ISO this grade certified. So it means it has followed some standard. It follows some standard specification, right? So it is just the way of specification. So my dear student, you can give the feedback on this comment section. Those who are live can give the feedback in the comment section as well, if you like the lecture or not. And we are going to meet again at 1 p.m. So after 1 hour, we are going to see each other again. Okay. So if there is any doubt, you can please ask me. If there is any doubt, you can please ask me. If there is any doubt, you can please ask me. I will be more than happy to answer you. I will be more than happy to answer. If there is any doubt, please do ask me. Please do ask me. Please give your feedback on the comment section and like, share and subscribe the GATE Academy. Okay. So please come in all the sessions. This is a 6-day lecture series. Every day we will cover 4 hours, 2 hours, 10 to 12 and 1 to 3. Okay, 1 to 3. Okay, and after the 6 days, steam turbine, gas turbine will be covered in all the respect. Compressible flow will also cover. So we are covering everything what is added with respect to the fluid and thermal sciences. Okay, in the next topic, flow through fluids. Our heading is flow through nozzles. In that flow through nozzle, we will be covering the compressible flow as well. That will be covered. Some people are thinking that is a part of fluid mechanics. That is a part of combined in fluid mechanics thermodynamics. Okay. So as I said, I already have covered that in Hindi in the GATE Academy Hindi channel. So do subscribe that also. Go and see that video also if you are comfortable with the Hindi language. If you are not comfortable with the Hindi language, if you are not comfortable with the Hindi language, we will have the compressible flow discussed in English language at the GATE Academy English channel as well. Okay, so let's say thank you very much. Thank you very much. Please do subscribe the GATE Academy and let's see you at 1 o'clock for the next lecture at the GATE Academy. Okay, thank you. You can please subscribe, you can please share, and you can please give your feedback in the comment section. Thank you very much.